Picture two enormous cosmic armies, each made of thousands of galaxies, charging toward one another faster than a rifle bullet. In the chaotic aftermath, the stars streak onward unscathed, yet something invisible is flung violently aside, leaving a ghostly bruise across space. Just days ago, NASA unveiled the James Webb Space Telescope's razor-sharp portrait of this bullet cluster. And for the first time, Webb's near-infrared vision traced that hidden mass with surgical precision. Where luminous galaxies and fiery gas part ways, Webb's map reveals a cold, dense silhouette that carries the bulk of the cluster's weight. Even after the cosmic crash, this silent majority is dark matter, the universe's most stubborn secret. Tonight we'll dive into Webb's discovery, see how it tightens the mystery, and ask whether the darkness holding our galaxies together could one day tear the cosmos itself apart. So grab a seat, dim the lights, and let's follow those hidden footprints across intergalactic space before they vanish into the void. Cut to a gleaming gold mirror the size of a tennis court unfolding, like origami 1.5 million kilometers from Earth. This is the James Webb Space Telescope, or Webb, a 6.5-meter segmented eye that gathers nearly 6 times more light than Hubble and drinks in wavelengths our eyes can't see, from 0.6 to 28 microns. Suspended behind a 5-layer sunshield colder than Pluto, Webb's cameras operate at about 40 Kelvin, letting it pick up the faint warmth of infant stars, dusty galaxies, and crucially for today's story, the ghost glow of intra-cluster starlight. 4 instruments share the workload. NARCam snaps ultra-sharp images. NER-SPEC dissects light from up to 200 objects at once. MIRI dives into longer mid-infrared wavelengths. And FGS NIRIS keeps Webb locked on target while doubling as a slitless spectrograph. Together, they turn the telescope into a cosmic CSI kit, capable of mapping both what shines and what hides in shadow. Since its first light in mid-2022, Webb has rewritten textbooks on everything from exoplanet atmospheres to the universe's earliest galaxies. Now, its infrared vision is exposing where most of the universe's mass truly lurks. Inside dark scaffolding, we can trace only by the stars stripped from their homes. Ready to see the evidence? Just 3.8 billion light-years away in the constellation, Carina lies the bullet cluster, 2 galaxy swarms that smash together at nearly 4,500 kilometers per second. Imagine ramming 2 cities the size of the Milky Way into each other and watching the streetlight stars glide through while their gas clouds flare like airbags. X-ray images from Chandra first showed that hot glowing gas, ordinary matter, lagged behind the galaxies after the impact, hinting that something heavier had shot ahead. That something became dark matter's smoking gun, because its gravity still bent background starlight long after the crash. Webb's 2025 Deep Field View sharpens that classic picture. With NERCam's resolution, astronomers counted thousands of background galaxies and tracked how their light is stretched, strong and weak gravitational lensing. The new map resolves at least 3 distinct clumps of invisible mass aligned with the brightest cluster galaxies, plus a faint ICL trail of rogue stars, tracing a dark matter filament between the main and bullet components. Most telling, Webb confirms the dark matter stayed with the galaxies, not the gas, even after one of the most violent collisions since the Big Bang. If dark matter particles interacted through anything except gravity, those clumps would smear out or drag behind, yet they remain razor sharp. The lesson? Whatever dark matter is, it barely notices itself, let alone normal matter, tightening the constraints on exotic theories. Pull up Webb's fresh, deep field of the bullet cluster, and you'll notice something remarkable. Background galaxies look like candle flame smudges, curved and stretched into arcs. That distortion is no camera glitch. It's gravity lensing, the telltale fingerprint of mass. Webb's NIRCam identified 146 separate strong lensing features, triple the number Hubble ever spotted, giving researchers the densest data set yet for weighing the cluster. Next, astronomers layered those arcs onto a map of light coming from intracluster stars, rogue suns flung into space during the collision. Because these orphan stars drift freely through the combined potential of both clusters, they act like cosmic glitter, outlining whatever is tugging on them. Webb's images show that shimmer lining up almost perfectly with 3 concentrated blobs of unseen mass. In other words, the intracluster light is tracing dark matter, even in this chaos. To make the invisible visible, the team overlaid Webb's lensing-derived mass map, in blue, onto Chandra's X-ray view of superheated gas in pink. The result is a cosmic jigsaw where the blue clumps stay glued to the galaxies sailing ahead, while the pink gas trails behind like a sonic boom shockwave. That separation, first hinted at by Hubble, now measured with Webb's 10 times sharper eyesight, puts a new, tighter upper limit on how often dark matter particles can bump into one another. Essentially never. If they interacted even weakly, those blue blobs would smear out or stick to the gas. Instead, the edges are knife-sharp. Webb also pushes the weighing game to larger scales. By combining weak lensing signals from thousands of faint background galaxies, scientists could track the mass profile from the cluster cores all the way to their outskirts, a span of more than 3 million light-years. The curve matches simulations where 85% of the mass is invisible cold, dark matter, and only 15% is ordinary atoms. Any funky, self-interacting dark matter models now have a much smaller playground left. Bottom line, Webb hasn't found cracks in the dark matter paradigm. Instead, it has sketched an even crisper silhouette of the cosmic scaffolding, daring physicists to explain what this silent skeleton is actually made of. For decades, physicists hoped dark matter might betray itself by bumping, however gently, into its own kind. If those collisions happened, the bullet cluster would be the crime scene. During the smash-up, dark matter snowplows in each cluster would have slowed down, lagging behind their host galaxies just as the X-ray gas does. Webb's new lensing map shows the exact opposite. The unseen mass stays welded to the galaxies, no offset larger than about 10,000 light-years, 1/10 of previous limits. That razor-thin separation translates into a cross-section for dark matter self-interaction of sigma over m less than or equal to 0.3 square centimeters per gram, the tightest constraint yet from any cosmic merger. In plainer words, if 2 dark matter particles the size of bowling balls passed within a kilometer of each other, they'd almost never collide. Whatever they are, they're more ghostly than neutrinos, more aloof than photons sliding through plate glass. And that deepens the nightmare scenario for theorists. Popular ideas like dark photons, axion-like particles, or supersymmetric WIMPs predicted at least trace interactions, leaving fingerprints Webb could spot. With each non-detection, the candidate zoo shrinks while the cosmic inventory, 85% of all matter, stays stubbornly invisible. Even modified gravity alternatives struggle. Webb's mass map matches cold dark matter simulations almost line for line. So far, dark matter has answered every telescope with silence. It neither glows, scatters, nor slows. The universe is telling us, in effect, that its dominant ingredient is a perfect shadow, felt only by the curvature of space-time itself. That's the first chilling confirmation Webb delivers. The mystery is alive and well, and we understand it even less than we feared. When astronomers speak of large-scale structure, picture a universe-sized spiderweb. Galaxies are the dewdrops. The strands themselves are built almost entirely of dark matter, with just enough starlight sprinkled in to betray their presence. Webb gave us our clearest look yet at one of those strands in 2023, when NIRCam caught a 3 million light-year filament linking 10 young galaxies only 830 million years after the Big Bang. The whole structure is anchored by a blazing quasar that lights it up like a street lamp in a fog, turning a formerly invisible bridge into a glowing signpost. That discovery shocked theorists because computer models expected such mature scaffolding to appear hundreds of millions of years later. If dark matter highways were already fully paved so early, it means gravity latched onto those invisible particles with ruthless efficiency, funneling gas into galaxies at breakneck speed and kickstarting star formation long before cosmic dawn should have brightened. Fast forward to the modern universe, and the pattern still holds. Dense, galaxy-rich knots sit where filaments intersect, while vast voids, regions tens of millions of light-years across, grow emptier by the day. The culprit is dark energy, the mysterious pressure that's accelerating cosmic expansion. Recent Webb-calibrated distance measurements confirm the expansion is running about 8% faster than textbook models predict, deepening the so-called Hubble tension. If dark energy stays constant, every cluster outside our local group will eventually zip beyond our light horizon, leaving Milky Way-sized islands marooned in blackness. But fresh surveys hint the force might evolve, opening futures where the fabric of space either tears itself apart, a big rip, or coasts gently to a halt. Either way, the cosmic web we admire today is living on borrowed time, stretched ever thinner across an accelerating void. Imagine pressing fast forward on the night sky. With every passing billion years, the glimmer of distant clusters dims, then winks out entirely as space itself stretches between us and them. That runaway expansion is driven by dark energy, the unseen pressure that already outweighs matter 2-to-1. If it keeps its current pace, galaxies beyond our local group will cross a point of no return about 100 billion years from now, their light forever unable to reach us. Yet some models say dark energy may grow stronger. In that big rip scenario, the Hubble expansion rate accelerates without bound. First clusters, then individual galaxies, then star systems, and finally atoms are torn apart as space-time pulls itself to shreds in roughly 20 billion years. Other ideas predict the opposite, a slow fade in the cosmic push, leaving the universe to coast toward a quiet, thinly populated eternity. Webb's early measurements of ancient supernova and quasar light echoes hint the expansion is running a few percent faster than classic models predict, adding tension to the debate and reviving theories that dark energy might evolve with time. Either way, the lesson mirrors the bullet clusters. Most of the cosmos operates behind an invisible veil, and just as dark matter silently holds galaxies together, dark energy silently pries them apart, writing an ending we can model in equations but can't yet fully comprehend. The deeper Webb looks, the more that ending feels unavoidable, and the lonelier the far future sky begins to seem. Webb has sharpened the mystery, but the cavalry is en route. NASA's Nancy Grace Roman Space Telescope, Hubble on wide angle, is in final assembly, scheduled to launch between late 2026 and May 2027 on a Falcon Heavy. Roman's 300-megapixel wide-field instrument will shoot vistas equal to 100 Hubbles at once, recording weak lensing shapes for hundreds of millions of galaxies. Its high-latitude survey should nail dark matter clumping to within 2% across 12 billion years. Roman will also test a cutting-edge coronagraph, plus an unprecedented census of far-flung supernovae, giving fresh cross-checks on dark energy. Europe's Euclid, already sending first deep field troves, adds near-infrared lensing over a third of the sky. March 2025 data dumps delivered 26 million galaxies and pristine Einstein rings, previewing an eventual billion galaxy atlas with sub-percent precision. Ground reinforcements come from Chile's Vera C. Rubin Observatory. First light images, released June 2025, kick off the 10-year legacy survey of space and time, scanning the southern sky every few nights and catching dark matter fingerprints in motion. Together, Roman, Euclid, Rubin, and future CMB maps promise a decade when dark stops meaning unseen and starts meaning mapped in 4K for both mass and motion mapping. Dark matter and dark energy remain unseen rulers of the cosmos. Webb's view of the bullet cluster proves the skeleton is real, rigid, and unfathomably aloof, while the universe's expansion shows the fabric is already unraveling. Yet every sharper image, every tighter limit, drives us closer to answers. So, keep looking up. The night sky is not just beautiful, it is a puzzle begging to be solved, and we're finally gathering the pieces. Thank you for watching. Subscribe for more content.